Welcome to lesson number 4 and our focus on balancing reactions. Our lesson objectives: analyze reactions for conservation of mass and balance chemical reactions using coefficients. The law of conservation of mass states that in all chemical reactions there is a conservation of not only just mass but also energy and charge, meaning whatever goes in must come out. So what we start with is what we end up with. So the number of atoms of each element must be equal on both sides of the equation. So for example, if I start off with my reactants on this side of the scale and I have 5 atoms of zinc and 5 atoms of oxygen, and then a chemical reaction occurs where I rearrange these and form a new substance on the right hand side, notice that the number of atoms did not change. I had 5 zinc atoms on the left, I have 5 zinc atoms on the right. And the same thing for oxygen, 5 on the left and 5 on the right. So the number of atoms does not change, and therefore the mass does not change. We show conservation of mass on both sides of this reaction. So let's look at this reaction right here. H2 plus O2 makes H2O. This is an unbalanced equation, and it does not show conservation of mass. And let's see why it doesn't. So if I make some models here, so I have 2 hydrogens for the diatomic hydrogen, 2 oxygens for the diatomic oxygen here, and then H2O, which is 2 hydrogens and 1 oxygen making 1 water molecule. This does not show conservation of mass. Just look at the atoms. They are not the same on both sides. I have 2 H's on the left and 2 H's on the right. I have 2 O's on the left and only 1 oxygen on the right. So the number of atoms are not equal. If they're not equal, the mass isn't equal. So let's look at the mass values. We have 2 grams for the hydrogen and 32 for the 2 oxygen. Add those together, we get 34 on the reactant side, but only 18 on the product side. So how do we show conservation of mass? We used a balance equation. And so in order to balance it, I put 2 moles of hydrogen and 2 moles of water. And how does that balance the equation? Let's see. So by doing 2 moles of hydrogen, I have 4 atoms of H on the left, and then doing 2 moles of water, I have 4 atoms of H on the right. So the H's are balanced out. And let's look at the oxygen, 2 on the left and 2 on the product side on the right. So the number of atoms are balanced, and if they're balanced, the mass is balanced. So let's look at the mass. I have 2 times 2 is 4, plus 32 gives me 36 grams on the reactant side, and then 2 times 18 gives me 36 grams on the product side. So conservation of mass can be shown by just counting the number of atoms and seeing if they're the same on both sides. So let's check your understanding. Can you analyze reactions for conservation of mass? So now let's look at these balance equations. How do we balance equations? We do that with coefficients. These are the big numbers out in front, and they represent how many moles, for example, I have of a substance. Note that we never change the little numbers here called the subscripts in the chemical formula. We never touch those. We're only adding coefficients, which means we're just going to have more than, let's say, the 1 that's represented. So what are the steps for balancing equations? Well, the first thing you want to do is we want to balance the atoms on both sides using the smallest whole number coefficients. If for some reason you end up with not the smallest whole number, make sure you reduce. And then go back and check to see if each atom is balanced on both sides, meaning that you have the same number of atoms on both sides of the reaction. So let's see an example. So initially, in this reaction, if I want to see if it's balanced, I want to look and see how many atoms I have of each type on both sides of the reaction. So on the left side, I have 2 N's and 2 H's. On the product side, I have 1 N and 3 H's. So obviously that's not balanced. So let's look at the hydrogen. So I have 2 hydrogens on the left side, but 3 on the right. So how do we get them to be the same or equal? Well, I look at or find the least common multiple of 2 and 3, which happens to be 6. And then I say, okay, what can I put out in front here as a coefficient that when I do that times 2, it's going to get me 6. And what can I put out in front of here as a coefficient times 3, it's going to get me 6. So we'll start here with the first one. So I can put a 2 out in front. So if I have 2 NH3 molecules, then 2 times 3 gives me 6. And then I can put a 3 out in front of my hydrogen, and 3 times 2 gives me 6 H's. And then because I had a 2 out in front here, 2 times the 1 N gives me 2 N's. And then I already have 2 N's over here. And so now you look and see the number of atoms on both sides of my reaction. The reactant side and the product side are the same. We have 2 N's on the left, 2 on the right, 6 H's on the left, and 6 H's on the right. And because we're the same number of atoms, then we know the mass is conserved. Let's look at another example. We'll do the same thing. So in this reaction, let's first see if it's balanced. So I have 1 aluminum, I have 1 copper, and 2 chlorine on the left. I have 1 copper, 1 aluminum, and 3 chlorine on the right. So this is not balanced, and it's the chlorines really that aren't balanced in this reaction. So same situation as before, we have 2 chlorines on the reactant side and 3 chlorines on the product side. So how do we get them to be equal? Again, find the least common multiple of 2 and 3. In this case, it's the same, which is 6. And then I'm going to put a coefficient in front of both of these to get that number to 6. So put a 2 in front of the AlCl3. So 2 times 3 gives me 6. And then I'm going to put a 3 out in front of this compound, and 3 times 2 gives me 6. And now by putting a 3 here, now I have 3 times 1 gives me 3 coppers. I only have 1 copper on the right side, so I can put a 3 in front of that to balance it. And then if you look back here, the 2 gave me 2 aluminums, but I only have 1 on the reactant side. So I can put a 2 here to balance out my aluminums. And then just double check, make sure everyone is equal on both sides. So on the left-hand side, I have 2 aluminum, 3 copper, and 6 chlorine. And on the right side, I have 2 aluminum, 3 copper, and then 2 times 3 gives me 6 chlorine, and they are balanced. Okay, let's see another example. H2 plus O2 makes H2O. We have 2 H's on the left, 2 on the right, 2 O's on the left, only 1 on the right. So the oxygens are not balanced. So if I have 2 here and only 1 here, I could put a 2 in front of water. Now I have 2 molecules of water. That's going to give me 2 times 1 gives me 2 oxygens. So I have 2 O's on the right and now 2 O's on the left. But now let's look at the hydrogen. Since I have 2 here, 2 times 2 gives me 4 H's on my product side, but only 2 right now on the reactant side. So what could I put in front? I could put a 2 coefficient. 2 times 2 gives me 4, 4 H's, 2 O's, 2 O's. We have a balanced chemical reaction. And lastly, if we have a group of elements that are the same on both sides of the equation, like we have NO3 here and NO3 here, we could treat them as a whole unit and balance them out instead of balancing out the N's and the O's individually. Either way is going to get you the same answer, but just a little bit faster. So if you look at this NO3 in parentheses, there's a 2 subscript, meaning there's 2 NO3 units. Over here, I only have 1. So I could put a 2 out in front, and now 2 times the 1 NO3 gives me 2 NO3s, and now the NO3s are balanced. And now let's look at the rest of the things. So 2 AGs, I only have 1 AG, 1 silver on the right side. So I could put a 2 in front of that. And then 2 times the 1 Cl gives me 2 Cls, and on the reactant side I have 2 Cls. And then lastly, 1 Ba on the reactant side and 1 Ba on the product side, so we know we have a balanced reaction. So just a faster way to treat these substances when we have this kind of grouping of atoms that are the same. Let's check your understanding. Can you balance chemical reactions using coefficients? At this point, you should be able to analyze reactions for conservation of mass and balance chemical reactions using coefficients.